All right, so in these practice problems, we're going to be looking at a couple of different things about thermodynamics as far as the calculations are concerned. And you're going to notice that a lot of these values I seem to just have at hand, and that's because I do. In the textbook, it makes reference to quite a few tables that you should familiarize yourself with, especially Appendix C in your textbook, okay? So when you're like, well, where did he get that number from? If I don't tell you, I probably just got it from that table. When you're working these problems, you're probably going to be using those tables too. So just kind of keep that in mind. So the first question we're going to look at, and quite a few of the questions, as a matter of fact, are going to involve the Haber process. So the Haber process is mentioned quite frequently in this chapter in your textbook, and actually in some other places as well. And it is the process by which we make ammonia. It was invented by, I believe it was Fritz Haber, a German guy around the turn of the 19th or the 1900s. Yeah. So the process that forms ammonia is nitrogen gas plus 3 hydrogen gas yields 2 ammonia gas. And this question asks us to find the delta S, the change in the entropy, for the synthesis of ammonia through the Haber process there at 298 Kelvin. Now, from the reading, from the lecture, from the textbook, whatever, we know that the delta S of the system is going to be equal to, all right, the sum of N times the entropy of the products minus the sum of the coefficients times the entropies of the reactants. So I've just written that here. You can see I've already put in the coefficients, right? So here is where I got ammonia's coefficient from, and from hydrogen, they're the same, all right? So just pulling it from those coefficients. Once I have those things, right, I'm going to get my entropies, probably from a table, right? And I'm just going to plug and chug. Now, the nice thing about this stuff is that you can literally just plug and chug in your calculator. Once you get those formulas down, it really does become pretty easy to solve these. One thing that you want to look out for is you want to make sure that units are properly canceling. Infamous things that happen on the AP test, they give us kilojoules or something like that when we need joules per Kelvin for entropy. So just kind of keep that in mind. S should always be in joules per Kelvin, right? Joules over Kelvin. So anyway, I plug that into my calculator. I do the products over here. Then we have the sum of the reactants on the right in these brackets, and that gives us a delta S of the system of negative 198.3 joules per Kelvin. Now, there is some logic to this, right? And we looked at in the other video trying to make sense of this in terms of logic. So I have a decrease in the total number of gas molecules in this process. And you're like, well, wait a minute. What do you mean? Well, if I look at the system as a whole, right, and I just divide it into the reactant side and the product side. Well, on the left side, I have 4 gas molecules, right? Because we have 1 molecule of nitrogen reacting with 3 molecules of hydrogen gas. And on the right, I'm only making 2 molecules. And so I have a decrease in the total number of gas molecules. And so I have a negative entropy. And that makes sense, right? That's logical. In problem 2, we're going to continue to work with the Haber process. But now I'm going to ask you this. I'm going to say, okay, find delta H of the reaction, find delta S of the surroundings, and then find delta S of the universe. This is pretty much the order that we go in when we find these things. The system, then delta H, then delta S of the surroundings, and then delta S of the universe. That way, the math flows pretty well. I've got the formula up there for you again. So for the delta H of the reaction, I'm going to solve that pretty much exactly like I did problem number 1, except obviously now I need to put enthalpy values in instead of entropy values. So that's the only real difference there. Delta H is going to be in kilojoules, all right? And I'm going to end up with negative 92.38 kilojoules. Notice that this cancels and this cancels, and so it's just 2 times negative 46. And that's it. That's delta H of the reaction. This is an exothermic reaction. So we can say that the reaction gives off heat, but it's better to say the heat is absorbed by the surroundings, okay? Now, for delta S of the surroundings, I'm going to use my, the equation that I talked about in the other video, where instead of Q reverse, we're just going to use negative delta H of the reaction in place of Q sub reverse over temperature in Kelvin. All right, and that's going to give me 92.38 positive, right? Because here it's negative. So I have a negative times a negative. So that's going to give me a positive divided by 298 Kelvin. And that's going to give me 0.31 kilojoules over Kelvin. But I know that would be wrong because if I'm looking for an entropy, right, I need to have it in joules per Kelvin. All right, so I'm going to convert the kilojoules per Kelvin over to joules per Kelvin, and it would be 310 joules per Kelvin. Now, the entropy of the universe is really easy to calculate now. We calculated the delta S of the system in the first one. We just now got delta S of the surroundings, and so we're just going to plug those things in. So in the previous question, we got negative 198.3 joules per Kelvin plus 310 joules per Kelvin, and we see that the delta S of the universe is positive 112 joules per Kelvin. Now, what can we conclude from that? Well, two things. Number one, if we get a positive number for the delta S of the universe, we know that that is going to be a spontaneous process, because for any spontaneous process, the entropy of the universe must increase. It must be a positive value. And the second thing we could just say is, hey, this reaction, the Haber process, is going to spontaneously move towards the formation of product at 298 Kelvin. So those are the two conclusions we would make there. All right. I know that was a bunch. You may need to pause it and go back and watch little pieces of the video again. You might need to work the, problems for yourselves. Make sure you're taking time to do that as we work through these practice problems. All right, let's look at number 3. Is the following reaction spontaneous at 25 Celsius? We have phosphorus reacting with chlorine to make phosphorus trichloride. All right, well, if I'm going to look for spontaneity, I need to look for the delta G of the reaction. And we're going to find delta G by doing 4, which is the product right here, all right, times the delta G of PCl3 minus delta G of P4 and delta G of PCl2, or sorry, of just Cl2. So 4 moles for the left, 1 mole for the P4 on the right. And you'll actually notice that Cl2 is actually going to go to 0 when you look up the delta G in the chart. You'll see that that's just a 0 value. So I can leave it out for the rest of the reaction. And so there's my delta G. Again, pretty simple. All right, we're just solving it based on the equations that we learned in the lecture. We're just, learning how to identify the parts and plug them in. So I have products on the left, reactants there on the right. I do get a negative value for delta G, so my answer is pretty simple. Hey, I got negative delta G, so when Gibbs is negative, I know that the reaction is a spontaneous reaction. Let's look at number 4. Calculate the values of delta G for the Haber process at 25 Celsius and at 500 Celsius. All right, what's the difference in this problem and that problem? Well, the problem is we don't have 25C for 500 degrees Celsius, right? The first temperature is fine, but both temperatures, right, we have two different temperatures. So we got to use our non-standard equation. So we've already calculated delta H and delta S for the Haber process. So I'm just going to pull those numbers back from problem 1 and 2. So delta G at 25 is going to be negative 98.38 minus 298 times negative 198.3, and I'm going to convert that over into kilojoules. All right, make sure you convert that over into kilojoules for our delta G here. Why do I have to convert it to kilojoules? Well, I can't subtract kilojoules in the first unit minus joules in the second unit, right? Because the Kelvin is going to cancel. So I got to make sure I'm subtracting like terms. I'm going to use the same exact approach, all right, for the delta G at 500 degrees. But something's got to change, right? And that's pretty obvious what's going to change. It's going to be the temperature. And in this case, the temperature is the deciding factor between these two outcomes, right? Whether or not it's spontaneous or not. So when I plug this in at 25 degrees Celsius, I'm going to get a negative 33.3 kilojoule value for the Gibbs free energy. And at 500 Celsius, I'm going to get 61 kilojoules. So how do I interpret that? Well, pretty simply. At 25 degrees Celsius, the reaction is spontaneous. At 500, it's non-spontaneous. And that's what I want to pull from a delta G number. I want to be able to calculate whether something is spontaneous or it's a non-spontaneous reaction. Now, we're going to take a little minute here, and I'm going to give you a little mini lecture on Q, the reaction quotient. Now, I would recommend that you go read chapter 15.6, section 6, and chapter 15 rather. This is something that we'll come back to when we get to equilibrium, but because it ties in so well with thermodynamics, I usually hit it here and then I hit it again later because it can be a little confusing the first time you get to rate. So this kind of helps us as we analyze it. So let's look at what this says. It says that Q is found by substituting reactant and product concentrations into an equilibrium constant expression. So this is how we find Q. And this is just a set of fill in the blank kind of recipe here. You've got little a's, little b's, little c's, whatever, little d's. Those are your coefficients. And the big letters are obviously the actual compounds. So if you plug the concentrations of each reactant on the bottom and each product on the top, and you raise the concentration to the power of their balanced coefficient, which you'll see in a second, then you get Q, as long as the reaction is at equal, or Q is found, K is when the action is at equilibrium. Q is when it's anytime. All right, so anytime in the reaction. It doesn't have to be equilibrium. Sorry, I got my P's and Q's crossed there. And it says it right there in the next line. So Q lets us know what the equilibrium, what the reaction quotient is at any point in the reaction. K is pretty much the same thing as Q, but K is only found when a reaction is at equilibrium. So you wait until the reaction reaches equilibrium, then you plug in your coefficients, raise them to the powers of their balanced equations, and that gives you K. Sometimes it's K sub C. That's another way that we occasionally show that as the equilibrium constant there. Now, when we know K, we can kind of predict things that are going to happen to the reaction. That's something that we'll learn a lot more about when we get to kinetics. So in general, what you want to know about K is this. If K is a really big number, then you're predominantly making products. When K is a really small number, well, then you have mostly reactants present. If K and Q are the same thing, you know the reaction's at equilibrium. When Q, remember the equilibrium constant we find at any point, is greater than K, then you've got too much products. The concentration of product is too great, and the reaction is going to shift from the right to the left in order to kind of approach equilibrium. When Q is less than K, then the concentration of products is too small, and the reactions will shift left to right. All right. Now, there's a lot of different ways you can try to remember this. I just usually remember Q, then K, and it's going to shift opposite of the way that the greater than or less than sign points. So in this case, right, we're going to shift from the right to the left, right, back that way. All right. In this case, we're going to shift from the left to the right. So it's just opposite of the greater than less than sign. You can also just memorize it, right? Either way. So that's Q and K. So in this question, we're going to say, all right, calculate delta G at 298 K for the reaction mixture of 1 atmosphere of N2, 3 atmospheres of water, and a half an atmosphere of NH3 for the Haber process. So again, there's the Haber process. Well, the first thing I need to do is I need to find Q, all right? And I want to find Q, and so I look and I say, all right, well, I only have one product, so I only need one number on the top. I have 2 reactants, so A and B can stay on the bottom. So I take their concentrations, so the amount of gas that's there, so in this case, the pressures, 1 atmosphere, so on the bottom there, to the 1 power, 3 atmospheres to the 3rd power, right, because there's 3 waters. And I just realized, wait, what's going on here? This should not be H2O. typo. I'll fix that. Anyway, 3 to hydrogen's power, there we go, to the 3, and obviously 0.5 to the 2 because that goes to ammonia. When I plug this in, I'm going to get a Q value of 9.3 times 10 to the negative third. Now, the second thing I want to do is I want to find delta G. Now, you'll know that delta G prime in the notes that we already took is equal to delta H minus T delta S. And so I plug that in. I've already done that calculation, right? And we get negative 33.3 kilojoules per mole. So I have delta G prime. I have Q. So the last thing I need to do is find delta G. Now notice there's a big difference between delta G and delta G prime. So delta G equals delta G prime plus RT ln of Q. And this was at the very end of the lecture notes for chapter 19. Well, I have those values, so I just need to plug them in, right? Delta G prime, we already found, right? R is 8.314 joules over moles Kelvin. I have the temperature. I'm going to convert the joules right here in this value over to kilojoules so that I can add like terms, right? Kilojoules over moles. Kelvin's going to cancel. Joule is going to cancel. I'm going to be left with kilojoules over moles, right? There I have my like terms. I'm going to multiply that by the natural log of 9.3 times 10 to the negative third. That gives me a negative 44.9 kilojoule per mole value. Now I can compare those two things, right? I can look at it and I say, all right, well, what's going on in my reaction? Well, the value is becoming more negative. I went from negative 33 to negative 44. So as far as a number line is concerned, I'm getting further away from zero in the negative direction. That means there's more driving force to produce ammonia, right? Because there is greater pressure or greater reactant pressure, compared to the product pressures in our product, right? We have way more pressure on the bottom half than we do on the top half. A half an atmosphere of product has been made, but 4 atmospheres of reactant is present. So kind of think about like Dalton's law of partial pressures there, kind of bring that together. Now, what if I wanted to find K for the Haber process? Well, we already know that delta G prime is negative 33 kilojoules per mole. We already found that. Now let's rearrange that delta G equation and find K. So I briefly mentioned that in the lecture video, but I really didn't talk about how we would do that. And so here it is. At equilibrium, we know that delta G equals 0. So if we set delta G equal to 0, then we can exchange Q for K because at equilibrium, Q and K are equivalent. So then I have a formula that lets me rearrange it, right? I can move stuff around. So in this case, I subtracted the RTLN of K to get it, onto one side, and I just solve for K. When I solve this for K, I'm left with natural log of K equals delta G prime over negative RT. And so in order to get rid of the ln, I just set that side as a power of E. E is on your calculator. It is, let me find it. Second natural log gives you e to the x, and you can plug that in. Now, I like to solve these problems in 2 steps once I have my equation. Also, just as a side note, I think this is on the constant sheet. If it's not, you can just memorize the equation for K. You don't have to solve for it every time. Anyway, I like to solve it in 2 steps. First, I like to solve my exponential side, and then I just like to set e to that answer. So negative delta G prime over RT. Well, I convert my delta G over to joules per mole. That way I can divide out the joules, the moles, all right, just like that. And the kelvins go away too. So Kelvin on bottom, Kelvin on top, mole on bottom, joule, joule. There we go. So everything cancels out. I'm left with a unitless number, which is what I want. And then I just punch in my calculator, e to the 13.4. And in this case, I get K is equal to 5 times 10 to the 5th. K is really big here, right? So let's go back a little bit. When K is big, all right, we can expect products to predominate. When K is big, products predominate. Okay, so let's go forward. And there we go. K is large. The products are favored. We're mostly making our our products, in this case, ammonia. Okay, so those are a bunch of practice problems. That's kind of the look at the calculations we're going to be doing. These are not hard calculations. I want to stress that entirely. Like thermodynamics gets a bad rap that it's really difficult to figure out what to do. It's really not. Just take your time, all right? Think about which equation you need to apply. Use Appendix C, use the table in Chapter 19 to get your values, and then just plug and chug. I know that you guys are capable of that. Now, there is one last point I want to make about thermodynamics and the calculations that you're making. Thermodynamics will tell us the direction a reaction is moving. It will tell us the extent of that reaction, right? Big K or little k or whatever. It gives you nothing about the rate at which it occurs. That is a completely different study. That's kinetics. We're going to get to rates and we're going to get to kinetics, but do not confuse a spontaneous reaction as a fast reaction. It's not necessarily true, all right? Iron nails rust spontaneously, but it takes them a long time, right? On the other hand, if you manipulate the temperature and get a match head to a certain, a certain temperature, it will spontaneously combust. That will be a rapid reaction. But just because something's spontaneous does not mean it has to happen very rapidly. So you can find spontaneity or non-spontaneity, but that doesn't tell you reaction rate. It doesn't tell you speed. Okay, so that's a really important point that I want to make sure we don't get confused. All right. Now, go through this video, watch the practice problems a couple times. Again, familiarize yourself with Appendix C. All right. Work the practice problems, or the problem set rather, that I've given you. And if you have questions, let me know so I can help you. All right. And I will see you guys in either a Google